Okay, good morning, everybody. Let me start by thanking the organizers for inviting all of us to this lovely place. It's really fun to be here. It's a nice workshop, and what I like most, it brings together two different communities that should talk to each other because there's a number of things that touch both of us. This talk is about coherent neutrino scattering, specifically on the CONUS experiment where we have been heavily involved. So coherent neutrino scattering is actually an interesting process. A neutrino scatters by the exchange of a Z boson, not on the quark as you usually learn when you do particle physics, but on the whole nucleus, given the fact that the wavelength is so long that it's not resolving nucleus. The charge that is relevant is this combination here. It's 1 minus 4 sine squared theta w, which is about, it's tiny, so it's mostly the number of neutrons. It's proportional to the number of neutrons, and it requires very low momentum such that a nucleus recoils as a whole. Important is then the coherence length. So in order to see the nucleus as a whole, you have to take the energy low enough. That means you have to be below 50 MeV or something like that. Otherwise, you're not coherent. That means, of course, you have a lower cross-section, and you have to think about how to compensate that. And the answer is to go to very high neutrino flux to compensate the loss in the cross-section. The cross-section, differential cross-section, looks like this, and there shows up this factor n squared, so coherence enhances things drastically. If you take n equals 40, like for a germanium target, then n squared is 1,600, means a detector that usually would be 10 tons shrinks down to a few kilograms. So we talk about, in coherent neutrino scattering, also about small neutrino detectors, and there's a competition who has the smallest neutrino detector in the world, so to say. Next, you have different paths. One path is to use low-energy neutrinos from accelerators, pion decay at rest. There are different flavors produced from the decay of the muon, etc. It's a well-defined flavor, etc. There's a higher energy than let's say for the other experiments for reactors. That means that they are close to decoherence. Means you see the form factor not fully coherent, which is good, as we'll argue in a second, but also is of course making your experiment not a fully coherent experiment. If you want to be fully coherent, you have to go to low energies, and that's reactors. You have lower energies then, and that's good. Here's the spectrum, and we just heard a discussion about these uncertainties. Note that the spectrum is actually a vastly varying function. That what people usually discuss in reactor experiments is folded this flux with a cross-section, which is like E squared. That's why I get this bump around 4 or 5 MeV. So it's the uncertainty in this slope in the flux that people discuss. And you see it's a log scale plot, so no wonder that at high energies there are some uncertainties because you're talking about a small part of the flux actually in total. Anyway, so there's different flavor components, which is nice. The low energies of reactor means that you talk about recoil energies in the range of hundreds of electron volt, as low as you can. Means it's a challenge to detector technology. And the complementarity in flavor and energies also, I will argue later on, has some very interesting synergies between these energies and also by itself. So it's an interesting route to take. There's no duplication whatsoever. This led us to the formation of the CONUS experiment. We combined 3 developments, 3 factors to improve. First of all, we go to the lowest detection threshold. We push the germanium detector threshold very low, and I will tell you later in a second how low it goes. It's based on some R&D that actually came out of our involvement in Gerda Legend, etc. There's the best background suppression that you can get. There's some technology that we call virtual depth that helps there. You know, to operate the detector on the surface and create conditions as if you are deep underground, because that's your enemy in the background. And you go to the highest neutrino flux you can get, means you want to get as close as possible to the most powerful reactor. That led to this CONUS experiment, which essentially is only us, which is fun because the collaboration meeting is every Tuesday. You take a cup of coffee and talk. And there's 2 guys actually from the reactor company. There's a physicist working at the reactor providing us a level of insight in the details of the reactor that you can only dream of, and we can make use of that. They're both physicists, so it's really a very, very strong combination. The reactor site is the Brokdev reactor in Germany, north of Hamburg. It has a thermal power of 3.9 gigawatt. It's one of the strongest reactors in the world. There's only 4 or 5 reactors which are more powerful. If you are at 17 meters, like we are, means you sit down here. This is the reactor cross-section. This is the reactor. This is this almost 4 gigawatt core that applies essentially all the electricity for Hamburg. And we sit down here very close underneath the basin with spent fuel and a lot of water, which adds to our shielding. So the amazing situation is that spent fuel is part of our shielding, if you want, etc., which actually is quite useful. And the neutrino flux is as high as it is. And you, of course, get this full flux that you have here, etc. and it's impressive. You have to worry about backgrounds. Is there any correlated background, like the neutrons when you turn the reactor on and off, and I will say more about this. And of course, once you have the background under control, you can say it's very simple, on versus off, and you're done. And that's actually what you can do, but then I will show you when you go into details, you find so many interesting things that you dig deeper and deeper and keep working on this at a level that's actually amazing. So the detectors are, we call them 4 germanium detectors, each about 1 kilogram. We call them CONUS 1 to 4. They sit in a very ultra-pure copper housing, are connected with a cold finger to a cryocooler. The cryocooler is a development which is very nice because it allows you to cool the detector without liquid nitrogen, which you can't use inside the reactor. There's safety regulations. And of course, there's a lot of R&D because there are pistons which are moving. You have to be careful to avoid any sort of microphonics, etc. And there's a very nice R&D behind that. And together with the producer, we actually succeeded to get pulsar resolutions of 85 electron volts and less. And experts know how this translates into a threshold, etc. And these cryocoolers are very nice because all you need is a plug. And then this was done in very close collaboration with Canberra. And then you do testing. This is the 4 detectors, and the pulsar widths are here that have been achieved. You do some calibration. You use sources, calibration sources to check that your detector does what you think. You check the linearity with different sources. You look by activating your germanium detector, put it over a day on the table, on the surface, activate it, and let the germanium 68, germanium 71, etc., isotope decay again. You actually can use this as calibration lines, and you can recalibrate if you just take the detector up and down again, etc. And this shows the long-term stability. And note this is 0.02%, this 2-band here. So it's very, very stable and very nicely under control. There's an interesting learning curve, and that paid off. Next is the shield. This is the so-called virtual depth. That's connected to our screening activities. We do low background screening, both in Heidelberg in our underground lab. That's actually these kind of detectors in shallow labs. And we operate the GEM detectors at Kernphysik, which are down there, which are the world's most sensitive detectors of that kind with a 10 microbecquerel per kilogram sensitivity. The problem we had, there's a big gap between these detectors, and whenever we needed more sensitivity than this guy here, we had to ship things to Kernphysik back, which was just a logistics problem. So we said, let's build something in between. And this is the Jovi detector, which is a Matrushka-like setup with many different layers, with lots of simulations on neutrons and backgrounds and testing, etc. And with this detector, we achieved in our basement in Heidelberg virtual depth as if you would be hundreds of meters underground. In fact, we could nowadays, inside this detector, we could repeat Heidelberg, Moscow, and Heidelberg. We wouldn't have to go to Kernphysik anymore. That's the achievement that's been achieved. So we could close the gap in the screening, but then the next thing, hey, great, you could use this on the surface to mimic something as if you're underground, and if you have to go to the surface, like a nuclear reactor, you can use it to reduce your background. That's so say what was done here, and then we termed this virtual depth, etc. Next, you build a detector, so there's a shielding. Exactly this idea. You use this shielding technique here, optimized for depth, so say. There's a different environment, so the layers change, but otherwise it's the same. And then you put these 4 PT coolers on the outside and detectors inside. There's some interesting things like this borated polyethylene. We use 99.9% enriched boron acid for that, which means there's a very high neutron capture cross-section, which makes the shielding even better than we had before, etc. And all that was demonstrated, so it was just the access to put it together. So we started in 2016, and already in 2018 we started data taking. It's been moving very nicely, and then we have collected data since then. The whole setup is about a 1 meter cube that you can put together like a puzzle. Then here are some pictures from the assembly and installation. There was a test assembly. You see the detector when it's still open. You see different layers here, the 4 detectors, the cryocoolers, etc. Then you take it to reactor. It's a very special environment. You have to get, for everything you do is a change of the operational procedures. You have, these guys helped a lot to get that done. Then you install things, you bring them down in this place, etc. Really very close to the reactor. And look at things. And this reactor is actually quite something because the neutrino flux there, in terms of power, means that's through the size of your body, 150 kilowatts of neutrinos streaming through, which means if it would be photons, it would evaporate. For comparison, the sun here on the Earth has 1 kilowatt of light per square meter and 7 watts in neutrinos. That's 150 kilowatts of neutrinos. That's just to give you a feeling how strong this neutrino source is. Then you find problems that you usually find when you operate a detector. One is, for example, radon, and solving the problems in a reactor site is not trivial because there's boundary conditions. You're allowed to do many things. And here you see the radon variation in the room. And then what we do, actually, we seal the detector as much as we can. And then in addition, we flush the detector with air. And you know that doesn't work usually. But we use actually the air bottles from the fire brigade. They keep a bunch of bottles underground, under the reactor, and refill them. So we use the old bottles. It's aged air. The radon has decayed, and that's the air we flush. And when you do the flushing, the radon is gone. Very nice, so you don't have to use nitrogen and boil off nitrogen and all that things that you do usually. Very nice technique, actually. So you're forced to new solutions, and sometimes they're actually very interesting. Then when you do analysis beyond the on-off idea, you find that a lot of things that enter. So they have to worry about backgrounds correlated with the source intensity, means you turn the reactor on and off. What else? There's neutrons, but there's other things you can think of. You have to really monitor the background rate if it's constant. Of course, you know that there's seasonal variations in muon flux and things like that, which you have to be careful. You have to, of course, do background modeling to check your knowledge from screening against what your model and what you see to check as a consistency, stability, etc. The environmental stability, reactors when they're shut off, there's refueling, there's 1,000 people coming in this reactor doing whatever here, and you want to take this data, so you have to be careful that they don't screw up something and which affects your detector, etc. You want long reactor on and off periods. That's something you usually don't get because the power company wants to make money, they run. So you have to wait for the off time. Sometimes they have off times which are not scheduled, etc. But there's something very nice in Brokdev. It's the only reactor in the world which is operated in a stupid way, so to say, because they balance the power against the windmills on the ocean. So there's a storm out there producing a lot of electric power, and windmills, they actually reduce the power. So there's variations of the power, which of course is great for us because you couldn't pay for it. So that's helping here. You want a high duty cycle, means your detector should be running all the time, and that is, so you have to shifting on the reactor side, which is fun. Of course, you control, monitor the detector stability, the efficiencies. One thing is the quenching, the amount of energy that you get out when a certain comes in. So there's some measurements, and we actually do also more on that, etc., to get this removed. It's actually one of the biggest error bars. And then, of course, you do your reactor modeling to predict the number of neutrinos that you expect to check against what you see. And last but not least, there's a lot of reactor physics. For example, when you ramp a reactor up and down, the spectrum changes, and we can tell you we see these changes. So there's the flow equilibrium in constant operation is one thing where people calculate the spectrum, but when you ramp the reactor, the spectrum is changing. The neutrino spectrum, neutron spectrum, things are changing, and you have to also look at this and can study it. So there's some important milestones. This is a plot of the reactor operation. In fact, it should be extended here. You see on periods, the dark green here, and the off periods. There's an optimization where we had such optimization. This was run 1, and this was actually this 2018 first run. We started off, and then the detector was running, and sure enough, the reactor power went down for a short time, for a week, and then came up, which was very useful because we had very quickly on-off, which was there. And just by looking at this on-off in this very moment, we were already able 2 years ago to say statistically only we see the effect. Then you start digging into the details, and I tell you more about this, etc. You see the blue curve is the power variation of the reactor. And every dip here, so say, typically in winter you see more dips, and summer it's more quiet, like here, etc. But there's reactor off was a refueling period, so they can compare before and after, how the fuel changes and things like that. There's a lot of details that you can talk about, etc. And of course, in Germany, as you know, all reactors will be shut off. Nuclear power will be phased out. This reactor, one of the last, will shut off in 22, and then we get a lot of off time to measure the balance of the statistics, so to say. But there's also, of course, a time left over here, and we are discussing how to optimize change detector to make best use of that, because that's a unique feature that they can run, and then at the end, just do a control measurement, right? As I said, most reactors want to run, and you don't get the off time that you need to compare with. Then, of course, we do our reactor simulations. We have in double show, in stereo, we are involved in that, so we have this modeling. So we do it, etc. So we do flux calculation for this room A48, where we are located at Brokdev, at this distance, etc., with that, etc. So to calculate the expected event rates without new physics means for a standard model, neutrino properties, etc. And I don't repeat the discussion. You have just heard a lot part of it. Note that we are mostly sensitive to the high energy tail of the neutrino spectrum, which is for the flux a certain uncertainty. But in the long run, this will also be beneficial for people that do flux calculations, because in double show uranium you have a mixed oxide reactor. In stereo, you have a highly enriched uranium reactor. And here you measure the high energy spectrum. So putting all this different information together should be very beneficial to clean up this reactor spectrum uncertainties, etc. So that's some value in that. Next, you can look at the expected signal strength. So we use different things as input, etc. We have a larger area under thermal power than most others, and I believe this error is justified. You can debate at some point. So there's good reasons for that, etc. The largest uncertainty in this experiment is the quenching factor, means how much energy you get out from the detector versus what the recoil deposits. And there's some measurements. So we show here the quenching factor range, let's say from 0.15 to 0.25, the threshold energy of your detectors. And of course, we're not over there, we are more on the left side. And the lines here show how many events you expect, so say, in a certain time interval from here. So it's clear you want to be at low threshold, and the higher the quenching factors, the better it is. You get 1,000 events in a certain time scale. If your threshold would be only 500 electron volt, and you would be down there, then you would be screwed because you would talk of one. So you have to push in that direction, and I can tell you we can do that. So next is the background level. You want to make sure that your background is low, that you understand. This is the real background level from one of the 4 detectors for over 214 days of time. That shows the counts per kilogram per day in kV. It's quite low, actually, impressively low, etc. And you see only, so to say, that first of all, you see that this virtual depth works, that this background is, so to say, very remarkable. After 1 year of operation, we see only 4 lines below 12 kV. These are these lines from these guys here, the recoils from the lines, etc. There's no hints for any other line or contamination, etc., which shows that the very low background show the reactor side is possible without contamination. In fact, I can dwell on that. The radio purity inside detector is better than many or most dark matter detectors underground laboratories. It's quite something to get this implemented in the reactor side. Then the background stability, you want to check that it's stable. Here you see the ratio, the germanium 68 and germanium 71 decay. The half-lives are here, 11 or 270 days. So what you see is here the measured values, these data points here. Green is the fit when you combine all what should be there, and the components that should be there is germanium 68 from surface activation, germanium 71 from surface activation. You see the different time scales of that decay, and you should also see that germanium 71 production, in situ production in the detector. And you see the components, they add up to the green line, that's what you measure. It means you understand the background very well. Radiance under control. There's little variation left. It has no impact on the low energy regime where we live doing physics. The decaying germanium isotope rate is actually seen and consistent with our background model with screening, etc. Hadronic showers close to the surface are fully negligible. First of all, there's our muon veto, and there's other reasons why we can factor them out, etc. And that's also why muon flux variations over time have a negligible amount in the end of the impact in the end of the day. So it's very nicely under control. Then the other thing to worry is neutrons, because as you turn the reactor on and off, there's of course huge amounts of neutrons in principle around. And the ones which you worry most are the ones which go with the reactor operation from the reactor core. But there's other ones in the walls, etc., and they are all outside the shield, first of all, and then the shield does what it does, reduce. So we did with the German Meteorological Institute, the Physikalisch-Technische Bundesanstalt, where the system, they called NEMOS, different size bonospheres in the room and mapped it out and reconstructed, eventually inverted the spectroscopy to determine the distribution space and energy, etc. And there's a very nice paper that came out of that. So we do full mapping, understand the neutron flux, and then we add on what we know about the shielding from outside to inside by extensive measurements in Heidelberg by using detectors in the inside, outside in our underground lab, so to have the extra ratio. And the outcome is essentially that the reactor-correlated neutrons inside the shield are negligible. So if you do all that and do the calculation, there's less than 1 neutron over the whole operation period that should show up in those detectors. It's quite some work, and the paper actually that came out of that is, I think, pushing the standards of these kind of measurements quite significantly. Then you want to check if there's a thermal power correlated background that's shown here. This is the bonosphere measurement with the PTB, etc. And here shown is the energy versus the count rate from reactor-induced neutrons down there, it's very low. The muon-induced neutrons, which you go after with your muon veto, are up there, etc. And in the end of the day, you see there's no on-off effect. There's a very low background. You control things. There's no power-correlated background from neutrons that you have to worry about. Then you have a background model. From screening all the components, you put it together. And I'll brief because the message is what we measure is fully consistent with what we expect from the components that we screen, and that's just demonstrating that. It's a fully consistent background model, etc. There's no surprise as it should be. What's the status there? The status is we have very detailed information meanwhile on the spectrum and flux, etc. This virtual depth actually is something that works very nicely, and the low background in the reactor side has been fully demonstrated. There was this very detailed study of neutrons that's been published here. There's a reactor-correlated background in the shield, which are the outcome. There's a number of studies with backgrounds, etc., in the pipeline, and unfortunately I cannot show them, but they should come out soon. There's a detailed background modeling on stability studies, etc. And as I said, we had this statistical accelerated neutrino 2018, and now, of course, you expect there's more interesting things to come. Unfortunately, I'm not allowed to tell you yet because there are some final tests and checks and issues that one has to work on. So more data, off data are there, and a very detailed analysis ongoing with lots of cross-checking. And there's a number of cross-checks we did, which I'm not talking about because that's going to be interesting when it's released. So then it's, for the last minute, good to think about the future. Some point you sit down and do a little calculation with your students. What if you went to 100 kilogram? It's in 3D, so 100 means from 4 to 100 is not a big detector, still a very sizable, small, feasible detector. And doing this calculation, there's what I call the BSM sensitivity, which is called delta S of S. This is table, which is now 2 years old. It says essentially they can reach, for normal numbers, something 10 to the minus 3 or even 10 to the minus 4 might be reachable if you're optimistic or not pessimistic. And then you can see what does it do for you. You can, for example, look for new physics in the form of NSI operators. NSI operators are the exchange of some particles so that there's neutrino fermion interactions, very much like the Fermi constant, but with a different strength, new physics with different strength. And you normalize actually the Fermi constant, means that these epsilons, since you normalize to the Fermi constant, epsilons are dimensionless numbers multiplied by the Fermi constant. So epsilon is something small times the Fermi constant. You can actually estimate it if you have a new particle exchange with mass m, epsilon is typically mw squared, which is coming from GF, over this new scale. So if the new scale is TeV and this is 100 GeV, you talk about epsilon 0.01. So if you're sensitive to epsilon 0.01, you talk about TeV physics, you're competing with high-energy experiments in that field. That's the exact cross-section. Of course, they're different of these epsilons. You have to be careful what your experiment measures in the end of the day. This was an exercise we did to show how powerful this would be. The 100 kilogram detector, 5 years of operation at a 4 gigawatt reactor. What's shown here is these diamonds are what Dune can do, and this color is what a detector of this type can do. So say with an optimistic or conservative estimate. And what you see, we can beat with such a detector the sensitivity of Dune. That's it, I would say. And hopefully it's cheaper, and it should also be hopefully on a short time scale. You can translate the epsilon in this case. This is TeV, that would be 10 TeV scale, so you're talking about this kind of high-scale physics. Next thing, very briefly, the Weinberg angle enters in the cross-section. So if you get very precise, you measure it. With a BSM sensitivity of 10 to the minus 3, you talk about delta sine squared θW of 0.006. 10 to the minus 4 is even 1 order of magnitude less. That's the typical size compared to what other people show in this low energy regime, and that's a consistency test of the standard model, sensitivity, new dark sectors, etc., kind of discussion. So it would be, with these error bars, you would be competitive in that field. That's what it says. Another one is you can look for new physics in the form of neutrino magnetic moments. That's the usual Dirac-Majorana standard model expression. If you have new physics in the TeV range, as argued by new physics at the LHC, etc., you expect enhancements, and the enhancement typically then down to 10 to the minus 14 or so from here. And of course, the best limit, so to say, is here. And you can do the exercise if you push on, how far can you do it? And here is shown, for example, the present limit. And if you take the exposure here, let's say you have 100 kilogram, and it can take 10 years, it would be yellow line. That's the limits you would get as a function of the threshold. So if you get a threshold of something between, let's say, 100 electron volt or below, then it's quite some improvement. Next is nuclear structure. That's where the synergy with Coherent comes in. By measuring these cross-sections and rates at different energies, you actually fully coherent in our case, and Coherent is partly coherent, you're actually mapping out nuclear form factors in neutrino light. Means you study nuclear physics with neutrinos in a way which was done before. You can do this so by comparing different energies and different ways to combine. And I guess Yuri will then say more about this, how you can combine the different isotopes. So there's a field where this connects back to nuclear physics and structure, etc. I think that should be watched and has interesting potential. It's also important for dark matter, Elena, for our usual roadmap that he showed. So if you push deeper and deeper, there's this so-called neutrino floor, which people hate because it limits your ability to discover dark matter. But after all, it's neutrinos. It's a signal. It's a solar neutrinos and atmospheric neutrino background, so to say, but it's a signal, and that's very good because it's exciting because that means you're doing high statistics neutrino physics. In fact, one of my guys, Wolfgang Hampel, was getting, when he first saw it, says, oh, it was almost crying. He said, I spent half my life to see neutrinos from the sun, now it's a background. Right? So it should be seen more positive, that's my attitude, and that's going to happen. Yeah, I shut it off with just giving you a list of, there's more things to be studied, etc. There's a very interesting discussion about what coherent scattering actually means. Is it the momentum transfer or the wavelength, as people say? There was a very interesting paper that we wrote where we discussed in detail and also the question, could you get to macroscopic coherence? Go beyond the nucleus, but the whole crystal, or so could you make it coherent? It's a nice exercise, what's limiting there, etc. And that was there, etc. You can also question the factorization, if that's justified in quantum field theory, etc. If the form factor language is still correct. There's a number of interesting theoretical questions coming along. The coherence length in QFT is an issue which is interesting. There's connections to dark matter models. In fact, I would say there's many. There's the idea of producing new fermions using coherent scattering, so you search for new particles, etc. There's effects of CP violation parameters in this coherent process that people discuss. There's safeguarding applications. Of course, such a detector can be used to safeguard the reactor. There's a reactor neutrino spectrum, as I mentioned. And there's these thoughts. I can tell you, we registered a patent coming out of CONUS, and I promise you this will be commercially successful. So neutrino physics is eventually producing even spin-offs that are useful. So let me summarize, and you can read it yourself. I think CONUS has started to move very nicely. It's a wealth of data, and it's just taking longer than you expect to analyze this. Our small collaborations are a huge benefit to move, to get the detector built and running, but it's a bottleneck in the analysis because you have to do a lot of work, etc. That's what you see partly. And of course, there's interesting effects that take time, as we will see. Okay, thanks very much.